Here we have our last set of examples for simplifying radicals. Concept is not terribly difficult, but it is new. It's a little bit different, so I wanted to make sure that I just had plenty of examples for you to look off of. And so let's do example 10. And this time let's do a cubed root of 80 x to the 5th y to the 7th zebra squared. And let's put a number on the outside. Let's put a 4 on the outside just to make it crazy difficult. Now in this scenario, what you're looking for, you want to have exponents that are raised to this index. Number on the outside is called the index. Inside they're called powers or exponents. So we'll start with the 80. 80 can be broken down as 2, which takes me to 40. In fact, I think I did this. This was what we did in the last example. Notice that I already broke the 80 down. In example 9, it was 2, 2, 2, 2, 5. There's no sense reinventing the wheel. Just think about how that's going to be broken down for this problem though, because I'm looking for a power of 3. So we were looking at this as 2 times 2 times 2 times 2 times 5. Same example I did a moment ago with example 9. And now when I'm looking at this prime factorization, I need 3 2's in order to get out of this airport security or jail or whatever you want to call that. So I could write this as 4 cubed root of 2 cubed. Now with what remains, neither one of those is going to get out. So if you want to multiply those at this point, you're more than welcome to do that. 2 times 5 would just be a simple 10. Then we go to our variables. You need an exponent of 3. You've got to match this index. This is called your index. These are your exponents. So I can call this x3 x squared, because that's x to the 5th. A y7 could be a y3 y3 y, because y3 y3 y is y7, and then I've got a z squared. Now it's time to move these out. As I move these out, this 2 can come out, but it loses its exponent. That's its ticket. So it becomes 4 times 2 is 8 on the outside. X cubed comes out as x. It loses its power, so it's just an x. Y, both of these y's can get out, so I'll call that a y squared on the outside. And that's it, which means that I would have a 10 left on the inside, an x squared left on the inside, a y left on the inside, and a z squared left on the inside. So I call that the cubed root of 10 x squared y z squared. Now earlier I was talking about when you bring variables out, you want them to be positive. That's only for when these indexes are even. So a square root, a 4th root, a 6th root, an 8th root, so on and so forth. If they're even indexes, you have to ensure that these are positive on the outside for a principal root. If they're odd indexes, so if the indices are odd, like this one, it's 3, I don't care whether that's positive or negative on the outside. It's allowed to be negative, so I can leave it go. I'm not terribly worried about you understanding that 100%. It's just that I want to introduce it because later on we do become a little more strict with that policy and we say, oh, these have to have absolute values. Right now, that's okay. If you're a little confused with that, we just want to get the experience of breaking these things down. Let's do another example. We'll go back to a regular radical. We'll call it example 11. And maybe we'll have 2 square root 175 a cubed b5 c squared. So as I look at this problem, I need to break that radical down. 175, I see a square in there. I constantly see money. I'm always thinking money. I'm thinking quarters. How many quarters is in a $1.75? 7. So with that 175, I can say 7 takes me to 25, and 25 is my square. So I could write this as 2 square root, there's my pair, there's an index of 2 here, 5 squared, 7. I go to my variables. Again, I'm looking for an index of 2, so I can call this a squared a, b squared b squared b, c squared. And we can see who's getting out. The 5 comes out. It can be joined with this 2. So 2 times 5 becomes a 10 on the outside. A gets out. B, B, and C. So I can call that A. BB would be B squared. 2 B's came out. C, radical, and everything that I did not underline stayed in. So I call that a 7AB. Now, as I was mentioning in the last example, this has an even index. It's an implied 2, so it's a square root. I can only have positive values come out. So I don't know that this A is positive. I have to put absolute values around the A. B squared is pretty much guaranteed to be positive. C, I don't know that that's positive, so it too needs a set of absolute values that go around that. This ensures the principal root. It says I guarantee that the answer is positive then. And notice that when I wrote my variables, they did go in alphabetical order. In this case, I did have to split the absolute values to say it goes here and there. And we can't be lazy and just say, well, let's just always put a big set of absolute values. We're testing to see if you understand what's positive and what's not positive, or possibly not positive. It's the exponents that are odd that have to have absolute values on them. And so I think that's enough examples. I hope that's enough examples. That's 11 examples on how to simplify radicals. Simplify radicals.